Okay, thank you for joining me. Today I'm going to be talking about a few concepts in the wonderful world of physics. In the first note, which is 3.1b, I'm going to be talking about different forces along the horizontal, okay, meaning left or right, west, east, forward, backward, those sort of forces, okay? Now, we're going to start with two types of the same force. So there's a friction force that can be applied to an object, and it depends on one property, whether or not the object is moving. If the object is moving, the friction force is very specifically called kinetic friction. If the object is not moving, it is called static friction. Okay, so the static friction prevents the object from slipping, whereas the kinetic friction is in the opposite direction to the slipping of the object. Okay, so I like to think of it this way: if you see an object that's already moving, then and friction is applied, it's kinetic friction. And if the object is not moving, if there is a friction force, it would have to be static in that case. So in this first example, we're asked to determine the net force, right here, acting on a bobsled when the athletes apply forces of 370 newtons forward and 410 newtons forward. Now, if you notice, there's two individuals here, okay, so 1 and 2, and they're each pushing on the bobsled. That's why you have two forces that are forward. Meanwhile, there's a force of kinetic friction, which means that this bobsled is already moving and it's in the opposite direction to the motion. So whenever you have kinetic friction, in that case, it would be opposite to the motion, and static would be in the direction of the motion. So you want to include a free body diagram. Now, a free body diagram is essentially a box that has arrows, and the arrows represent the forces acting on the object. In this case, it wants a free body diagram on the bobsled. Okay, because it says the net force acting on a bobsled. So you want to do a free body diagram on the bobsled. So what kind of forces are being applied? You got two applied forces forward and one kinetic friction force backwards. So I'm going to draw a free body diagram right here, and that free body diagram has two forces. One is, let me see if I can use a point. No. One is 370 forward, and the other one is 410. And then there's a 120 newtons backward. The net force is actually the sum of all the forces on an object. So there are three forces clearly here, right? One is applied, two are applied, and one is kinetic. Now, if I assign forward to be positive, then it's a positive 370, positive 140, and a negative 120 because that's in the opposite direction, it's backward. Once you do the algebra here, you get a net force on the object of 660 newtons. What I would say then, because force is a vector, what I would say is the net force is actually 660 newtons forward because I ended up with a positive number. So this is how I would calculate the net force acting on an object that has horizontal forces. I could have done the same thing with vertical forces, and that was the subject of 3.1a, which won't be discussed here, at least not in great detail. Okay, so now I'm going to show you two scenarios. So I could have these two scenarios where a car is the object and it skids while braking on a horizontal road. So you have to ask yourself what forces are applied to this car. So now, if we take into account both horizontal and vertical forces, and let's say the object, the car, is moving this way forward, but the acceleration is backward, well, then there's a kinetic clearly backward because it's slowing down. That's the whole point of braking. And you've also got a normal force that's up and a gravity force that's down. Now, the normal force is the contact force that the floor or the ground makes with the car's tires. It's always perpendicular to the direction of the the surface. So if the surface is horizontal, the normal force would be vertical. Gravity fights that, and so you have a balance in the vertical. But there is no balance in the horizontal. So the normal force and gravity do not affect the motion because they are balanced with each other. But the force of kinetic friction doesn't have anything to balance with in the horizontal. And so what it does is it causes the car to slowly slow down, because it's in the opposite direction to velocity. So if the acceleration is in the opposite direction of velocity, then the car is slowing down. Now, in this scenario, you've got a car that accelerates when a traffic light turns green. So the car is already stationary, right? In part A, the car was not stationary, it was moving, and then it started to brake. So that was a kinetic friction, right? But in this example, a car accelerates from rest at a traffic light that's red, it turns green, and it starts to accelerate. That's not a kinetic friction, that's actually a static friction. So the car pushes down on the ground, or pushes back on the ground pushes forward on the car, causing it to accelerate. And that static friction, because it's in the direction of the intended motion, then the velocity and acceleration are in the same direction, which causes the car to speed up in this case. Okay, so static would be not moving, kinetic is moving. Kinetic is opposite direction, static is in the same direction. Now, we can also talk about a system of objects, because here we only have one object, right? In this case, we talked about a car in two different scenarios. But I could have a system of objects. So for example, I've got a snowmobile and a sled. Now the snowmobile is attached to the sled by a cable or some sort of harness, something, and that causes a tension between the two, right? So let's read this carefully. So we got a snowmobile that's 650 kilograms, and that snowmobile up here in front experiences a drag of 150 newtons. Drag is another name for air resistance. Now, it also applies a tension of 370 newtons in order to pull a sled that's 55 kilograms, okay? So just to give you an idea, the snowmobile, right, is pushing down on the ground, pushing backward on the ground. The ground is pushing forward, and it tells you what force the ground pushes forward with. It's 3,900 newtons. And the sled over here experiences 84 newtons. There's a lot of information here, clearly, right? But since there's two objects of consideration, a sled and a snowmobile, I'm going to make two free body diagrams, two force diagrams, okay? So a sled has these forces. It's got a tension due to the fact that the snowmobile is pulling it. It's got kinetic friction because it experiences kinetic friction, the sled does. So it's got a kinetic friction 84 newtons backward. It's got a normal force, a contact force of 539, but where did that 539 come from? Well, the 539 up top came from the fact that it balanced in the vertical with the gravity force. The gravity is mass, which is 55 kilograms times 9.8. So you have the free body diagram of the sled, and you've got all the forces applied. Since there's a balance in the vertical, I'm not going to talk about the vertical. Instead, I'm going to try to figure out what's going on in the horizontal. I'm going to add those two forces together and get the F net for the sled. So look at that. I've got an F net for the sled, and I go 370 plus negative 84 because it's in the backward direction. So I get a total net force of 286 newtons, but if you want to account for significant digits, you have about 290 newtons forward. The snowmobile has an interesting scenario. The snowmobile is being pushed by the ground at a force of 3,900 newtons. The snowmobile is the only object that experiences the drag force of 150 newtons backward. Also, there's a tension between the sled and the snowmobile. It's also going to be 370 newtons, but for the snowmobile, it's actually backward because it's behind the snowmobile. And it still has a gravity and a normal, but the gravity is so much bigger for the snowmobile because it weighs more. Okay, it's 650 kilograms in mass, and so you multiply that by 9.8, you get 6,370 newtons. Now, if I do a net force for this object, in the same way, I'm only going to look at the horizontal because there's a balance in the vertical, and I end up getting 3,380 newtons. So accounting for significant digits, you have about 3,400 newtons forward. Now, that's the two objects separately. What if I wanted to account for the system as a whole? What I would do is I would merge all of these forces together, but there's something that I want you to notice. Because there's 370 newtons and they're in the opposite directions, these two red lines are going to cancel each other out, which is good news because then you have less forces to deal with. So what do I have here? I have FA, FD backward, FK backward, and two normal forces up top, two gravity forces in the bottom. If I combine them, this is the diagram I get. Okay, and if I want to do a net force on the entire system as a whole, both the sled and the snowmobile, then I only have 3,900 newtons minus 150 minus 84, and I'm going to get 3,666. And so if you account for single digits, you get 3,700 newtons forward. So that's the total net force. You could have also gotten it by going 290 plus 3,400. Okay. So basically, that is, in a nutshell, how to calculate the net force on a system or a single object, right? So now we're going to talk about Newton's laws. Okay, so I'm going to close these documents. And I'm going to open up Newton's laws of motion. Okay, so for Newton's laws of motion, there are three main laws. So there's three laws. There's Newton's first law, there is Newton's second law, and there's Newton's third law. Okay, so we're going to start with Newton's first law. Newton's first law officially is that when an object's velocity will not change unless acted on by an unbalanced force. So what balance means is that you've got all forces canceling with each other and you get a net force of 0. But that just means, Newton's first law just means that an object that has a 0 net force will continue in its motion, in its velocity, its constant velocity, unless another force enters into the system that causes it to no longer be balanced. Okay, so if all the forces acting on an object add up to 0, the object will not accelerate. But if I now introduce another force, let's say I have 4 forces to begin with, they all cancel. If I introduce a 5th force that causes it to not cancel, it will begin to accelerate and its velocity will change. That's all it means. We could also examine, objects that are on slants, right, on slopes. So you've got a box here that's at rest. Okay, so if it's at rest and it's on a slanted, slope, there's probably some sort of friction that's preventing it from moving. And in that case, because it's at rest and not moving, it has to be static friction. It also has a gravity force down, straight down. And so I can break this gravity force into two components, one perpendicular to the surface and one parallel to the surface. Now, there's a typo here. This shouldn't say F net. This should say Fn for F normal, because that's the contact force that an object has with a surface. Here I have a perfect balance if it's completely stationary. So basically, the component in the gravity that is perpendicular to the surface balances with the contact force of the surface, and the component of the gravity that is parallel to the surface balances with the static friction. Now, I have another scenario where I have a skier, and the skier slides down with constant velocity down a hill. In part A, I have a constant velocity of 0. In part B, I have a constant velocity that's not 0. And in this case, the only difference between these two diagrams is that this has Fs, this has Fk, and that's because the skier is moving and the box is not. So in both cases, you get a balance, which means F net is 0 and A is 0 as well. Now, what is Newton's second law of motion? So Newton's second law of motion is basically that the acceleration that a body experiences depends directly on the force, but inversely on the mass. What that means is if I increase the force on the same object, the acceleration is going to go up. But if I increase the mass of an object, if it becomes heavier and heavier, it's not going to experience as high an acceleration, even if my force is the same. So apply the same push on an object, but you've got two objects, one is less massive than the other, the more massive object will experience less of an acceleration. So I've got this equation to summarize Newton's second law, and that equation can be rewritten as F net equals ma. So let's use this equation for Newton's second law in action. You want to determine the net force causing a 206-pound cyclist to accelerate from this speed to this speed in that many seconds. Now, I want the net force, so I need F net. But in order to do that, I need the mass and the acceleration. Now, I'm given that you've got 206 pounds. So that's the mass, but in pounds. How do you convert it to kilograms? Well, in kilograms, that's going to be 93.636. You divide by 2.2. And you need the acceleration. How do you get the acceleration? Well, you've got initial velocity, a final velocity, and a time, delta t. So I can plug that information in to get the acceleration on the bottom left here. And once I have that, I can actually determine the net force. And after calculating, I end up getting 354 newtons forward. So that's a way of kind of combining kinematics on the left here with the acceleration calculation with the new dynamics calculations, F net. Okay, so I've determined the net force on a 206-pound cyclist. So we can also use the net force to determine a missing force in a system or in an object, right? So you've got a mass, 1.32 pounds, that is hanging from a string tied to the ceiling inside an elevator. You want to determine the tension in the string when the elevator is accelerating at that rate, 1.9 meters per second squared down. Now I'm going to call that negative 1.9 because it's down, but I'm going to draw a free body diagram. That's a good step one. So you've only got two forces here. You've got a tension up as well as a gravity down. Now, you can calculate gravity once again by going 9.8 times the mass, and I get 5.88 newtons. That's a given formula. And I'm just missing the tension force, so I have to actually determine that tension. But I do know what it accelerates at. So if I use F net equals ma, and the fact that F net is the sum of all the forces, I can build the equation in the second row here. So I can build this equation right here. So right here, I can build that equation. So I plug in negative 5.88 because I know that gravity is down. And I plug in that m is 0.6 kilograms because I have to, again, convert the 1.32 pounds into kilograms. And I plug in negative 1.9 for A, and I'm able to find Ft, and I have 4.74 newtons up. So this is a way of using Newton's second law and the stuff in the last note to determine a missing force. Now, we're going to talk about Newton's third law. Newton's third law says that for every action, there's an equal but opposite reaction. If there's a force between two objects, object B will apply force on object A that will be equal in magnitude but opposite in direction. So you have to think of it this way. B is applying a force on A. A will respond in the same way as B did on itself. It would respond back on B, but in a different direction, in the opposite direction. So let's use a skydiver example to describe this scenario. Okay, so Newton's third law, we want to describe the forces between a skydiver and the Earth. So we know that the skydiver experiences a gravity. So that gravity is due to the fact that there's the Earth, right? The Earth pulls down on the skydiver. The skydiver actually responds by pulling up on the Earth in the same strength that the Earth is pulling on him. And so you end up getting this Newton's third law. Now, students might be confused. How could a skydiver be pulling on the Earth? The Earth doesn't move. Well, the skydiver is pulling, but you have to remember that the Earth is way more massive than the skydiver. So the Earth isn't going to move because the skydiver's pull is not strong enough. If it moves, it's very infinitesimally small. So, and that goes back really to Newton's second law, because over here we talked about how if you have a higher and higher mass, your acceleration is less and less. So the Earth's mass is, I believe, 5.98 times 10 to the 24 kilograms. That's a huge mass. And so the skydiver pulling on the Earth won't have that much of an effect as opposed to the Earth pulling on the skydiver. So that's an example of Newton's third law of motion. Okay? Now you can also have a similar example, but with a sprinter. The sprinter pushes down on the ground, backward on the ground, using a static friction force, and the ground pushes forward on the sprinter with equal but opposite direction friction force, static. And it's that force that causes the sprinter to actually accelerate forward. So this is an example of, or a short lesson on Newton's laws of motion, as well as on the balancing of forces in a free body diagram. I hope you enjoyed this. If you did, leave a like, comment, subscribe, and I'll see you in the next one. Bye.